This is a video for AQA Discrete Mathematics, Graphs and Networks, section 1.5, where we're looking at Kruskal's algorithm for finding minimum spanning trees. In an earlier video we looked at Brims' algorithm for finding minimum spanning tree, which starts at a particular point and then the tree grows from that point. But what I'd like you to do now is to just sort of think about what would you do if you had to solve this problem in your head. So what might you do first, do you think? And then what would you do after that? Which edges would you choose and why would you do it? Now most people who are asked this question say, well, I'd start by using the smallest edges. And this is sort of an intuitive way of doing it, and then just keep building up. Kruskal's algorithm basically does exactly that. It starts with the smallest edge and then looks at which edges we can add, progressively getting larger. So it starts with the smallest and goes through. There's only one thing that really you have to be aware of, and that's forming a cycle when doing this. So Kruskal's algorithm says select the shortest edge in the network. So if we look at this one, we'd start off by selecting the edge of length 5. So we start off here, and what I tend to do is to just indicate that I'm using that particular edge on my diagram, and then of course you would write it down. So this is the order we're selecting, which is WL, and it's of length or weight 5. The algorithm then goes on and says, well, now find the next shortest. So the next shortest edge we can see is the 7. So that's L to C, which is 7. And then we keep doing that until all the vertices have been connected. So the one important thing is that we do not create a cycle. So we now look at the next shortest edge, which is CW, length 8, but of course CW would form a cycle, so we'll say not CW because it forms a cycle. Then we go on to the next one, and the next largest one is 11. So that's the next one to add. So SR of 11. Now we've got a choice now of SC or CR, and once we get a choice we can do that whichever we want. So let's go for SC, which is 12. And that gives us our 4 that we need to produce the minimum spanning tree. Remember that if we've got 5 nodes, as we have in here, we need 4 arcs, and we've achieved that. So the only thing we could have done is at that point there, it could have been S to R, and that would also have produced a minimum spanning tree. So here the minimum spanning tree is not unique. Kruskal's algorithm is greedy in the same way as Brims was, so it always takes the best option that it can at any given stage. The only thing left to do now is to say that the weight of the minimum spanning tree is obviously the total of these. So we'll say weight of minimum spanning tree is equal to the total, which is 35. Kruskal's algorithm then starts with the shortest arc, or the arc of least weight, so that we can see easily that one is DE, and it's of length 18. The next one is GF 21, and then after that DC at 22, and then we've got a choice at 24 of either CE or BD, but CE is going to form a cycle, so we'll say not CE because that's producing a cycle, but we will use DB size 24. We then go on to the next one. You'll see that that is length 26, which is EG. So that one comes in EG at 26. Now working up, we've got 28 next at EF, but we can't use that because that would produce a cycle, and CF also would produce a cycle. So we can say not EF or GF because they would produce cycles. Next one is of length 30, and that's AC, so that's going to be added in, AC length 30. And then 31AB, but we can't use that because it produces a cycle, so we'll say not AB. And then finally GH length 33 completes the tree, so that GH 33, and that's our complete tree. We know it's complete. We've now got in there a total of 7 arcs, and there were 8 nodes, and therefore we've got 1 less arc than node, so the tree must be complete. So the main thing to remember here is that you've got to make sure you don't produce a cycle. You must also look around and make sure you're getting the shortest arc possible at each stage. And then the final thing to do is to say that the weight of the minimum spanning tree is the total of these, so the total weight is equal in this particular case to 174. It's difficult to use Kruskal's matrix on a matrix because it's quite hard to spot when these cycles are going to be forming. The common errors, well, the usual sort of things really, not choosing the shortest arc to add, so missing out a shorter one that you could have used. Forming a cycle by accident, that's quite difficult. If you keep track of what's going on your diagram, you can see when the cycles are being produced, so you shouldn't really suffer that one, but it is a possibility. Forgetting to record the order of the arcs as you're going along. Well, yeah, if you do that, then you've got to go back to the beginning and start again, so it is tricky. And also forgetting to mention why you're not putting in an arc, so it's not showing enough working. And then finally forgetting to state that weight at the end. So Brims and Kruskals, then we've looked at, they both produce minimum spanning trees. Both are greedy algorithms, but you notice that Brims and Kruskals will add the arcs in different orders. If there's more than one minimum spanning tree, then it's possible that they will produce different ones, but obviously the weight of the trees that they produce will be the same. In Brims, you're always joining a new vertex to an old one, so it's a tree which grows. However, with Kruskal's algorithm, it's possible to add in a completely new arc which isn't joined to your existing one, so we could say that you're joining a new vertex to a new one, or you're joining an old to an old, which then produces the connection. And we said that Kruskal is difficult, if not impossible, to do on a matrix, and so it's good for small networks, but it's not so easy to program. We saw that Brims could easily be programmed or adjusted to work with a table, and therefore can be used for larger networks. Well, that's the end of this video, and indeed the end of this section of videos on graphs and networks and looking at minimum spanning trees.